Hello and welcome to the second of our two-part tropical cyclone structure video series. In this one, we're going to take a look at the idealized response in terms of the structure, specifically the in, up, and out portion of the tropical cyclone circulation, which we dubbed the secondary circulation, and to some extent the primary circulation in terms of its maximum sustained near-surface wind speeds. The idealized response of those features to applied heat forcings, such as you might see associated with thunderstorms, keeping in mind that the thunderstorms act as a conduit for the surface heating to be able to be spread within the vertical, and to momentum forcing, such as you might see with an upper level trough of low pressure. So let's dig in. So just to remind ourselves, we have our tropical cyclone secondary circulation here, where we have this enthalpy or entropy or moist static energy or theta E gaining inflow layer here near to the surface with deep tropospheric ascent here within the eye wall that then gives way to outflow at higher altitudes extending out to larger radius. And so we ask the question in the context of this lecture, what happens if we have enhanced convective warming, such as perhaps you pass over a warm eddy of sea surface temperature, and so you're able to gain even more enthalpy, or perhaps for some reason you're able to have a convective burst near or inside of this radius of maximum winds. So what would be the response of this in, up, and out circulation to that particular forcing? Or conversely, what if we encounter a source of cyclonic momentum? Perhaps not here at 120 to 200 kilometers radius, but rather several hundred kilometers radius away from the center of the tropical cyclone, such as you might see with a mid-latitude trough or tropical upper tropospheric trough or something of those natures. So keep in mind what we're looking at here in terms of this idealized response says nothing about the thermodynamic environments in which the cyclonic momentum or the kinematic environments which force warming in the form of thunderstorms are present. We ignore the effects of ventilation. We ignore all of those aspects, vertical shear tilting the vortex and leading to asymmetric vertical motions. None of that's included here. We're looking at the very idealized forcings associated with warming and cyclonic momentum sources, nominally in the middle to upper troposphere within the tropical cyclone environment. So way back at the beginning of the semester, we introduced the Kuo-Eliason equation to describe the Hadley cell circulation. And on the first homework assignment, we said that there was an analog, the Sawyer-Eliason equation, which would describe the tropical cyclone secondary circulation. So now we want to describe what this Sawyer-Eliason equation looks like. The first thing to note is that there's no partial derivative with respect to time anywhere here in this equation. That means we cannot use it to make a prediction. We can only use it to diagnose what is happening. In particular, we're diagnosing the vertical velocity and the radial velocity, so the up-down and in-out components of the velocity as a function of heat forcing, and in particular how it varies in the radial or in-out direction, and momentum forcing, F, and in particular how it varies within the vertical or up-down direction. Now this response is modulated by three different coefficients, this n squared, b, and I that we see here. N squared is a measure of static stability. Note this dependence on the change of potential temperature with height. In general, unless you have a dry adiabatic collapse rate, which is highly atypical within a tropical cyclone, this is going to be a positive value. B is our measure of baroclinicity. It is related to the temperature gradient in the horizontal, which in this case is the in and out direction, the radial direction. While this is not zero, to gain our most general of insight, we can typically neglect the baroclinicity. And then I is a measure of inertial stability, and it's kind of complicated. We have radius, tangential wind here as in terms of a partial derivative with respect to radius. We also have tangential wind and radius over here with a component from the Coriolis parameter F. This is always going to be positive, however. So we are always inertially stable, we are generally statically stable, and weakly baroclinic enough to be able to neglect the B, which really helps because then this first term boils down to just W, and this second term boils down to just U, very similar to what we saw for the Kuo-Eliason equation. We define this heat source Q as positive for warming and this momentum source F as positive for cyclonic momentum forcing. So we can take a look at the responses. Say you put a heat forcing, as we see within this first row here, or a momentum forcing, as we see within this second row here, somewhere within the tropical cyclone, and used that equation on our previous slide to be able to deduce what W and what U would respond from or result from those. So in terms of a heat source, A, B, and C, we have the heat source here, here, and here. And in each one of these cases, you get ascent. These lines with arrows on them denote streamlines, and so there's always ascent through the heat source. We can view this as a response to try to eradicate the heat source. Heating leads to, in this case, positive heating is warming. Ascent, however, is associated with expansion due to adiabatic processes, and that expansion is a cooling process. So the heating creates ascent, and the cooling associated with that ascent tries to mitigate the effect of the heating. The momentum sources for panels D, E, and F that we have here are always associated with flow being directed from left to right. So we envision the center being on the far left side of each one of these diagrams, and this flow is directed outward, away from the center through that cyclonic momentum source. We can envision this as the response to try to eradicate that momentum source as well. We know cyclonic features are associated with convergence. So now here we have outflow away from and through this, trying to generate anticyclonic momentum within the tropical cyclone environment. And so consequently, this too is trying to get rid of the forcing that gave rise to it in the first place. Just as CAPE is used up by thunderstorms, so too is heating used up by ascent and momentum used up by outflow here. Now there are some differences. C and F are baroclinic cases where B is not 0, but A, B, D, and E are non-baroclinic cases. The baroclinicity causes the response to tilt outward in each one of these cases here, whereas it's upright in each of the 4 panels here at left. The difference between panels A and D and B and E is the inertial stability. When you have weak inertial stability, so a weak horizontal rotational constraint, the response is spread out horizontally. Whereas when you have strong rotational constraint with strong inertial stability, the response is constrained horizontally. It stretches out more vertically. So note how this is like a smushed pancake, whereas this is stretched out. This is more like a smushed pancake extending horizontally, and this is stretched out within the vertical as well. Static stability that we don't show here governs that vertical confinement for any given inertial stability. And we'll look at that here in just a moment. So we can look again at these responses to idealized forcings. We have a heat source here at left and a momentum source here at right. The dashed lines that you see here are lines of constant momentum, and where they are closer to each other, you have greater inertial stability. And so within this smaller radius region, with the center of the storm being here on the far left side, you have a larger inertial stability, and then as you get to larger radius, you have a smaller inertial stability. Note too that the sloped momentum contours are associated with sloped potential temperature contours. And so you get ascent through this heat source, but it is sloped outward somewhat. We can view this too in terms of the conservation of absolute angular momentum. Note that this ascent follows that momentum surface almost to a T. You have a circulation on the inside that does not cover very much radial distance, and a circulation on the outside that is very radially expansive, given the weaker inertial stability that is found there. Here, for our momentum source, we have outflow through that, and there is a weak tilt to that circulation. But what we see here from the packing of the dotted lines for the isentropes is that we have greater packing here near the tropopause, so we have higher static stability, larger n squared, and then at lower levels we have greater spacing between the isentropes and thus a reduced static stability. So the static stability, as we hinted at on the previous slide but couldn't show, limits the vertical extent of this response. Larger static stability, more confined vertical extent. Smaller static stability, greater vertical extent here, with again ascent through the heating, trying to eradicate the heating, outflow through the cyclonic momentum source, trying to eradicate the momentum source. So let's dig in a little bit more into heat forcing in specific. So in the top panel here, we have a measure of atmospheric motions. This is given in a quantity known as stream function, and this in particular, where you have positive values, denotes rotation in a clockwise fashion within the plane of this diagram. So clockwise means up here in Z, out here in R, down here in Z, and in here in R. And the opposite would be true for negative dash values here. The Z star equals 1 is the tropopause, Z star equals 0 is the surface, R star here equal to 1 is the radius of maximum winds, and 0 is the center of the tropical cyclone. So 5 is 5 times the radius of maximum winds. So we place this heat source at Z star equals 0.5, so halfway between the surface and the tropopause, and R star equals 1, the radius of maximum winds. We get primarily a response in the form of ascent through the heat source. We have positive stream function to the right, negative to the left, clockwise flow for the positive, counterclockwise flow for the negative. This gives rise to enhanced ascent through the heat source as we expect, which requires low-level convergence. Air comes in here, and upper level divergence. It spreads outward near tropopause level atop the ascent. We can then take a predictive equation, not the Sawyer-Eliasson equation, but one that we can generate from the Sawyer-Eliasson equation framework to use this to diagnose the surface wind tendency in terms of meters per second per day. Positive values indicate an increasing wind speed, negative values indicate a decreasing wind speed. So for this particular heat source, halfway between the tropopause and the surface at the radius of maximum winds, you increase the wind speed the most at and just on either side of the radius of maximum winds. You increase it less so as you go to larger radius, and then as you go toward the center, you actually reduce the wind speed. So you sharpen that vertical profile, or sorry, not the vertical profile, the radial profile of the tangential wind around the center of the cyclone at low levels in response to this heating. If you move this heating inward or outward, you may change this response a little bit, however. How, however, might we change it in that regard? So we're going to focus primarily on the left line or the left axis here, which is the maximum wind tendency in terms of meters per second per hour. How much would a particular heat forcing lead to the maximum sustained surface winds increasing over time? And all of these values are positive that we see here. On the x-axis, we're looking at different radii of where we place the heat source at the surface, from between 0 and 20 kilometers from the center, all the way out to 160 kilometers from the center. And for this simulated storm, the radius of maximum winds is at 30 kilometers away from the center here. It's these open circle, open square, open triangle lines that we are interested in. And the differences between them are not particularly important. You're looking at different vortex shapes, different vortex structures, but they're all broadly similar to each other. For placing the radius of heat source closer to the center of the storm, and in particular at and inside of the radius of maximum winds, you get the greatest positive response in the maximum sustained surface winds. You get a positive response no matter what radius at which you put it, but that radius of greatest response is within inside the radius of maximum winds. So this leads to the idea that if you can get heating associated with deep moist convection, such as a convective burst inside of the radius of maximum winds, you can intensify the cyclone more readily due to this heating than if that were, say, in an outer eye wall, as you might see here at like 140, 160 kilometers away from the center. So this response scales with that cyclone size, and that's really the differences between what you see here. These circles are for the broadest, largest vortex or cyclone. The triangles are for the smallest cyclone. And so the triangles lie on top of the circles inside of the radius of maximum winds. So a smaller cyclone where the heating is able to be more concentrated near to the center inside of the radius of maximum winds here gives you a greater response than a broader cyclone, although the sign and general shape is overall the same between them. However, this is just a highly simplified numerical model framework. Is this supported by observations? And indeed, it is. We have an idealized depiction of what you see from observations, and high-resolution full physics numerical model simulations, which are not shown, actually support this response. So here we have a set of intensifying cyclones, and here we have a set of steady-state cyclones. Y-axis is height from 0 to 15 kilometers, and then on the x-axis we have normalized radius. The center is at 0 on the far left side. R is the radius of maximum winds, 1 is the radius of maximum winds at the surface, 2 times and 3 times the radius of maximum winds. For intensifying versus steady state cyclones, the primary difference is where this convective burst is located. This convective burst is where your heating gained from the underlying surface in the form of enthalpy or entropy is going to be released over the deep tropospheric column near to the center of the storm. If you can get it at or inside of the radius of maximum winds, you get a stronger response in terms of the tropical cyclone. Whereas if it's at or just outside of the radius of maximum winds, this is enough to help sustain the cyclone, but not necessarily to lead to its intensification. And so in essence, we're really tying back to the idea of what thunderstorms are doing. It's just where you are mixing that enthalpy, mixing that entropy. Is it over a narrower region very near to the center, or is it over some broader region, either further away from the center or more expansive relative to the center? In all of these cases, you are going to have a positive response in the maximum sustained surface wind. It may be offset by other features or other processes in the steady state case, but if you can get it inside of the radius of maximum winds, you will intensify the cyclone more likely than not. You'll also bring this radius of maximum winds inward as that cyclone intensifies, which is what we see typically for contracting eye walls, whether they be primary or secondary in nature. So there is solid support from observations and from high-resolution numerical simulations of actual tropical cyclones to support this highly idealized insight from the Sawyer-Eliason equation. What about momentum forcing? So here again we have atmospheric motions on the top panel. 1 in Z star is the tropopause, 0 is the surface. R star 1 is the radius of maximum winds, 2, 3, 4, 5 times the radius of maximum winds, and 0 is the center. And we have the surface wind tendency here down at the bottom. Same radius coordinate, positive values denote increasing speed, negative values denote decreasing speed. So here, just like for the heat source, we place a cyclonic momentum source halfway between the surface and the tropopause at the radius of maximum winds. And we look at the stream function, and this gives us the same type of response. These positive values are denoting clockwise rotation. These negative values are denoting counterclockwise rotation in the plane of this diagram here. So the primary response is outflow, but in the lower troposphere here, we have enhanced inflow and enhanced ascent, whereas that's offset somewhat in the upper troposphere here. Typically, momentum sources are found closer to the tropopause, so you can extend this lower tropospheric portion over much of the depth of the troposphere, and this would lead some to say that if you place a cyclonic momentum source within the outflow layer, you're going to enhance the outflow, which means that you have to enhance the ascent and thus enhance the inflow, leading to a spin up of the tropical cyclone. And absent anything else, the bottom diagram suggests that yes, that is the case. If you have a momentum source, cyclonic momentum source at the radius of maximum winds, R star equals 1, you increase the wind speed throughout this region, but particularly inside of and at the radius of maximum winds. However, this completely neglects the shear and ventilation of cooler, drier environmental air that often accompanies momentum sources. We're going to come back to that point in just a moment. So we can look at this too in terms of some sensitivity to where exactly we place that momentum source. So in the top panel, we have the near surface height tendency. So you could think of this similar to the surface pressure tendency. And we have the near surface wind tendency here. So this is the same as the bottom panel on the previous diagram. And in fact, this solid black line, or sorry, this dashed line that you see here for r star equals 1 is the same as what we saw on the previous slide. Similarly here, this dashed line for r star equals 1 is the height tendency associated with that same momentum forcing. But we have two other lines in each case. R star equals 0.75, so if you place it inside of the radius of maximum winds, and R star equals 2, if you place it at 2 times the radius of maximum sustained winds. So note that for R star equals 2, this dotted line is a lot flatter for the surface height tendency and for the surface wind tendency. It still reduces height, still increases the surface wind speed, but not by as much and over a much broader area than for the momentum sources placed closer to the center of the storm. R star equals 1 versus R star equals 2 is very similar to each other, just that the response for R star, or sorry, 0.75 versus 1. It's just that the response for 0.75 is found somewhat inward of that for both height and wind. The peak of the solid line is somewhat further to the left on the diagram, so at a smaller radius than it is for the dashed line for placing it at r star equals 1. So if you place a momentum source at or inside of the radius of maximum winds, you get the greatest response, reduced near surface height and increased near surface wind speeds here. If you put them at larger radii, you get a weaker, broader response in both of those fields. However, the caveat, unlike for heat sources, which do have observational and numerical modeling support, there is not the same for momentum sources. Momentum forcing never occurs in isolation. It is always accompanied by vertical wind shear and ventilation of cooler, drier environmental air into the cyclone. So on the y-axis here, we have different values of cyclonic momentum flux. Negative values are anticyclonic, but we're really interested in these positive values, 0 to 20, cyclonic momentum forcing. So this is that F term in the Sawyer-Eliason equation. On the x-axis, we have shear magnitude from no vertical wind shear up to 20 meters per second over the depth of the troposphere here. And shaded within each box is an intensity change metric. It's not an actual value of intensity change, but it's more of a normalized value. Positive values indicate that you have a positive intensity change for the cyclones with a given shear magnitude and momentum forcing. Negative means that you have a negative intensity change for the tropical cyclones with that particular shear magnitude and momentum flux forcing. What we see here, if momentum flux forcing were the dominant factor, is that as you go upward at any given shear, you would expect to go from blues to reds. What you see instead is that as you go for any momentum flux from low shear to high shear, you go from reds to blues, which means that the dominant signal is not between intensity change and momentum forcing, but rather between intensity change and shear magnitude. Lower shear, predominantly red, so intensifying storms. Higher shear, predominantly blue, weakening storms. So those cyclonic momentum forcing in isolation would lead to a spin up of the tropical cyclone for the idealized configurations we've considered here. In practice, the cooler, drier air and increased vortex tilt associated with ventilation and vertical wind shear respectively more than counteract these effects and lead to a weaker tropical cyclone, all things considered. And that's where we're getting this extra black arrow here. So summarizing, the tropical cyclone's secondary circulation responses to idealized heat and momentum forces are to eradicate them. Ascent with cooling due to adiabatic expansion through the heat source, outflow with the generation of anticyclonic flow to eradicate the cyclonic momentum source that gave rise to that. For heat forcing, we do see support for the Sawyer-Eliason outcome in both observations and full physics high-resolution numerical simulations, highlighting in particular the benefit to cyclone intensity by getting the heating associated with thunderstorms, lofting that energy from the underlying ocean at or inside of the radius of maximum winds. However, the same is not true for momentum forcing. They're often accompanied by strong vertical wind shear and ventilation, and these factors dominate over any hypothesized response to the idealized momentum forcing. So this finishes up our discussion about tropical cyclone structure. You can view this particular lecture as kind of complementary to our previous series on tropical cyclone intensity change, kind of bridging between the two with the in, up, and out circulation, as well as the response to different heating and different momentum forcings. As we wrap this up, we have just one lecture series left, that on tropical cyclone motion. But until then, thanks for tuning in.